Tonight we're visiting what's left over when a star dies, and it's the strangest object anyone has ever found. We call them dead stars. Each one is a ball about 20 kilometers across, the width of the city you're sleeping in, and it weighs more than the whole of the Sunday. So now look at the bottle of water on your bedside table. Fill a bottle that size with the material a dead star is made of, and it would weigh about as much as the biggest mountain on Earth. It wouldn't sit on the table. It would go through the table, the floor, the bedrock, and keep going. And here's what nobody tells you about the leftovers. They aren't rare, and they aren't far away. There are hundreds of millions of them drifting through our own galaxy. We have found about 3,000, which means the nearest one is very likely a few dozen light years from where you're lying, which out here is next door, and not one person on Earth knows where it is. And here's the part that stops people the first time. Every single thing about them sounds invented. Their tallest mountains are 1 millimeter high. Their gravity is 200 billion times the gravity in your bed. They bend light so hard that you can see round the back of them, and the fastest of them turns 716 times a second, quicker than the blades of a kitchen blender, while keeping better time than any clock we have ever built. So what is one actually made of? What would that surface do to a spoon or a mountain or a person? And why do astronomers now believe that the gold in a wedding ring and the platinum in the car outside were made in the 2 seconds when a pair of these things touched? That's where we're going tonight. One layer at a time. From an armful of snow in your own hands down through a shell of solid iron to whatever is waiting in the middle, which nobody has ever managed to identify. If these journeys help you rest, a like or a subscribe is the kindest way to say so. And leave a comment with where in the world you are drifting off from. It's always bedtime somewhere. For now, dim the lights and settle in. I'll keep watch. Now, you're lying somewhere warm, held down by the softest gravity in this whole story, and we're going to the other end of it. Let's begin. Start with the snow, because everything tonight is in the snow. Picture a field of it after a still night. Ankle deep, blue in the dark, the kind that squeaks underfoot. It looks like a solid thing, and it is very nearly nothing. Gather up an armful and press it slowly between your hands, and you can feel the air going out of it, the bulk leaving, until what filled both your arms is the size of a plum and not 1 gram lighter than it was. Nothing was added. All that changed is that the emptiness left. And if you could keep pressing, past the point where hands work, past the point where anything on Earth works, the ball would go on shrinking long after it stopped being snow, because the ice in it is mostly empty too, and so is the water, and so is the stone under the field, and so are you. Tonight is the story of what is left at the very end of that pressing, and of the one place in the universe where the pressing is actually done. The pressing is done by a star, and a star is a very long argument between two forces that never agree. Gravity presses inward, always, patiently, trying to fold the whole thing into its own center, and heat pushes outward, and for millions or billions of years, the two of them hold each other in a standoff so steady that we call it a point of light and think of it as permanent. The heat comes from fusion in the core, hydrogen squeezing into helium, and that's what holds the weight up. Every second the star spends a little of itself to stay open, and every second gravity waits. Our own sun has been holding itself open like that for 4.5 billion years and has enough left for about 5 billion more. But a star much heavier than the sun spends itself the way a bonfire spends dry kindling. 10 or 20 times the fuel, and a lifetime 100 times shorter. It shines beautifully. It shines briefly. And then there is nothing left in it to spend. What happens at the end is a ladder, and each rung takes less time than the one before, and the shortening is the part that unsettles people. When the hydrogen in the core is gone, the core contracts and heats until helium starts fusing into carbon, and that phase might last 1 million years. Carbon into neon and magnesium, 1,000 years. neon into oxygen, about a year, oxygen into silicon, a few months, and silicon into iron, in the last hours of the star's life, takes roughly a day. Imagine a life where the first 80% passes in a slow, steady hum, and the final chapter arrives in an afternoon. Inside that star, layers are stacking like the rings of an onion, each shell burning a different element, each one denser than the shell outside it. And right in the middle, growing quietly, is a ball of iron. It's about the size of the Earth. It's hotter than anything you can picture. And it is the end of the road. Iron is the ash that will not burn. Every fusion step before it gives back more energy than it costs, which is why stars shine at all. But iron sits at the bottom of a valley in the way nuclear matter is put together, and fusing iron into anything heavier takes energy instead of giving it. So the moment the core of that star is iron, the heat stops coming. Gravity has been waiting the entire life of the star for exactly this. There's no heat coming from the middle anymore, nothing pushing back, and the standoff that held for millions of years ends in less time than it takes you to read this sentence. A ball of iron the size of a planet begins to fall into itself. Not slowly, not the way a building settles. The inner core falls at something like a quarter of the speed of light, which means 70,000 kilometers in a single second, and the whole collapse from a planet-sized sphere to something you could walk across in an afternoon takes about 1 second. And in that second, matter is asked a question it has never had to answer before. As the core squeezes past every density anything has ever reached, the electrons in it are pushed so hard into the protons that they simply merge. An electron and a proton, forced together, become a neutron and a tiny ghost of a particle called a neutrino. It happens everywhere at once, through the entire core, in a flash. The atoms that were there, iron atoms with their careful little architectures, stop existing as atoms. What's left is neutrons, packed shoulder to shoulder, wall to wall, with none of the roominess that made them atoms in the first place. And when that packing gets tight enough, something remarkable happens. The neutrons refuse. The collapse, which nothing had been able to slow, hits a floor made of neutrons that will not be pushed any closer together. And the whole falling core, moving at a quarter of light speed, bounces. That bounce is the loudest thing in nature. A shockwave tears back out through the star, and behind it comes something even more powerful, which is the neutrinos. All those electrons and protons merging released an unimaginable flood of them, and they pour out of the newborn core, carrying about 99% of the energy of the entire event. Think about what that means. The supernova, the flash that can outshine an entire galaxy of 100 billion stars for weeks. The thing bright enough that we can see it across most of the visible universe is the leftover 1%. It's the part that could not leave quietly. Almost all of it left as neutrinos, which are so unwilling to interact with ordinary matter that trillions of them are passing through your body right now, through your pillow, through the whole planet, without touching a single thing. Which raises a lovely question. If almost all of the energy leaves in a form we can barely detect, has anyone ever actually caught it? Once. In February of 1987, a star died in a small galaxy next door to ours, and about 3 hours before the light of that explosion reached us, 3 detectors deep underground on 3 different continents each recorded a tiny burst of neutrinos, 24 of them in total. 24 little sparks in tanks of water buried under mountains, spread across a handful of seconds. That's it. That was the whole harvest. But those 24 sparks were the first and so far only time human beings have watched the heart of a star collapse from the inside, in real time, before the star's own light had arrived to tell us anything. The people who found them in the data went back through it 3 times before they let themselves believe what they were looking at. And then there was a mystery that took nearly 40 years to settle. If the core collapsed, There should have been something left behind in the middle of all that expanding wreckage, and for decade after decade, nobody could find it. The dust in there is thick. The gas glows. People looked with radio telescopes and X-ray telescopes and found nothing definite, and a quiet worry grew that maybe the leftover had gone straight past being a star and become a black hole instead. Then in 2024, a telescope out at the second Lagrange point looked into the heart of that cloud in infrared light, which slips through dust the way a hand slips through smoke, and found argon and sulfur atoms glowing in a very particular, very excited way. Nothing makes atoms glow like that except a source of hard radiation sitting right there in the middle. The baby had been in the room the whole time. What it is, exactly, is a thing that had no name before it existed. Not ash, not a cinder. A neutron star, born at about 100 billion degrees, which is thousands of times hotter than the middle of the sun, and cooling faster than anything you'll ever meet. Within a single day, it drops from 100 billion degrees to around 10 billion, and it does that not by radiating light, but by sweating neutrinos out through its own body. It also comes out of the explosion moving. The collapse is never quite symmetrical, and the sideways kick it gets can be 400 or 500 kilometers per second, sometimes more than 1,000, which is fast enough that a few of them are sailing out of the galaxy altogether, alone, and will keep sailing for as long as the galaxy exists. So somewhere out there tonight is an object thrown out of a dying star at 1,000,000 miles an hour. And the strangest thing about it is not how fast it's going, it's how small it is. Let's put a number to it. A typical neutron star is around 20 kilometers across. 20. If you set it down on the ground next to a city, it would span the built-up middle of it and stop, and you could ride a bicycle from one side of it to the other in an hour if the ground under you were anything like ground, which it very much is not. From a distance, it would look like a dark, polished ball, a little bigger than a large town, the kind of thing you'd think you could push. And inside that little ball is more mass than the entire Sunday, usually about 1.5 times the Sunday. Every gram of a star that lit up half a sky, that had 100 million kilometers of glowing surface, is now inside something the size of a morning commute. Numbers like that slide off the mind. What does it actually look like, a mass like that, in a space like that? Let's do it with things you can hold. Take a mountain. Take the biggest one on Earth. All of its rock, all of its snow, everything from the seafloor up. Squeeze it to the density of a neutron star, and it would fill a bottle or two of water. You could carry the whole mountain in one hand, if the hand and the arm and the floor beneath you could survive the experience, which they could not. Now take the entire Earth, every ocean, every mountain, every city, the molten iron heart of it, all 7 billion trillion tons. At neutron star density, the whole planet becomes a ball roughly 300 meters across, small enough to sit inside a large park with room to walk around it, and the sun, which could swallow 1,000,000 Earths, becomes a sphere you could drive across in about 15 minutes. Which brings us back to that sugar cube. 8 billion people, at neutron star density, occupy about the volume of 2 lumps of sugar. Not the mass. The mass is unchanged. All 8 billion of us still weigh what we weigh, but the space we take up collapses to something you could lose down the back of a couch. And if you were to reach in and take out a single teaspoon of the stuff, one ordinary kitchen teaspoon, and set it on your bedside table, it would weigh about 1 billion tons. That's every car on the planet, roughly. All of them. In a spoon. Of course, it wouldn't sit there for even an instant. It would go through the table, through the floor, through the foundations and the bedrock and keep going. And even that isn't the real story, because the moment neutron star material leaves a neutron star and stops being crushed, it comes apart in a violent hurry. The stuff only exists under the pressure that makes it. Take it out, and it isn't a substance anymore. It's an event. There is one version of the smallness that stays with a person longer than the others. Work out the surface area of a neutron star, the total skin of it. Everything you could theoretically stand on. It comes to around 1,500 square kilometers. That is about the area of Greater London. The entire outside of an object heavier than the sun, the whole of its geography. Every place on it could be laid over one city and its suburbs, and there'd be no room left for a second city. There's no other place in the universe where so much of everything is folded into so little of anywhere. So why do these numbers feel wrong? Not surprising, wrong. As though someone had made an arithmetic mistake somewhere. It's because when we hear that something is unbelievably dense, we picture a substance. We picture lead, and then something heavier than lead, and then something heavier still. Some impossible metal from a story. And that instinct is exactly backwards, and taking it apart is the door into everything else tonight. Because a neutron star isn't made of heavy material. There is no heavy material. It's made of the same protons and neutrons as the water in your glass, the pillow under your head, and the snow on the roof, in the same amounts, with the same weights. Nothing has been added. Something has been removed. And what's been removed is almost everything, exactly the way it left the snow. So go back to the armful of snow, and then go one step further in. Put your hand flat on the bed for a second. It feels like one thing, doesn't it? Continuous, warm, definitely there. Now go inside it. Every part of your hand is made of atoms, and every atom is a nucleus with electrons around it. And the proportions of that arrangement are so lopsided that nobody draws them honestly, because an honest drawing would be a blank page. If the nucleus of one of the atoms in your fingertip were a grain of sand set down in the middle of a large room, the electrons belonging to it would be out past the walls. Everything between the grain of sand and the walls is nothing. Not thin air. Nothing at all. And the nucleus, that grain of sand, holds essentially all the weight. The electrons are so light that you could ignore them and be right to within a rounding error. So how empty are you? If you took every atom in your body and let the nuclei fall together with no space between them, the whole of you would form a ball about the size of one of your own red blood cells, and it would still weigh exactly what you weigh now. Everything you can see of yourself in the mirror, all of it is arrangement rather than substance. The volume of a person is not made of person. It's made of the distance the person's parts insist on keeping from each other. And that word, insist, is where this gets interesting. Because if we're mostly nothing, then the obvious question is the one nobody asks. Why doesn't your hand go through the bed? It isn't because the atoms are touching. Atoms never touch. When you press your palm against a wooden table, the outer electrons of your skin come near the outer electrons of the wood, and they push each other away with the plain electrical repulsion of like charges, which is a start, but it isn't the real answer. The real answer is a rule, and it's one of the strangest rules in physics. Electrons are not allowed to be in the same state as another electron. They can't share. Not because something stops them, but because the mathematics of what an electron is has no way to express two of them doing the same thing in the same place. Squeeze a lot of them together, and the ones that have run out of available states have to take on higher and higher energy instead. And the result is a pressure, an outward shove with nothing physical behind it. It comes from a rule about counting. It's stubbornness with a pressure gauge. That stubbornness has a name, degeneracy pressure, and it's the reason ordinary matter is difficult to squash. It's also, on a much bigger scale, what happens to most stars after they die. When a star like our sun runs out of fuel, it hasn't got the weight for the drama we watched earlier. It swells, sheds its outer layers into a beautiful glowing shell, and leaves behind a hot naked core about the size of the Earth, holding roughly half the mass of the Sunday a white dwarf. and nothing is burning in there. There's no fusion, no heat pushing outward, no source of support at all except that rule about electrons refusing to share a state. Gravity presses on an object the mass of half a sun, and the only thing holding it up is a counting rule. A teaspoon of white dwarf weighs a few tons. Our own sun will end this way, and so will roughly 97% of the stars in the galaxy, sitting there, cooling for longer than the universe has so far existed, held open by nothing but arithmetic. But arithmetic has a breaking point. Pile on enough weight, past about 1 4/10 times the mass of the sun, and the electrons finally lose. They can't hold, and gravity pushes them down into the protons, and every one of those merges into a neutron, and the whole thing falls to a new floor. Because neutrons have the same rule. They also refuse to share, and they hold out at a density about 100,000 times higher than electrons manage. So the collapse stops again, at a smaller size, on a firmer floor, and what you have then is the thing we're spending tonight with, which means a neutron star is not a strange material at all. It's the ordinary matter of your own body, with every gap closed and every rule pushed to its limit. And then the refusal beneath the refusal, holding, and here is the turn the whole night rests on. The density of a neutron star is, near enough, the density of an atomic nucleus. Not similar to, the same. So the whole object, 20 kilometers across, heavier than the sun, is essentially a single nucleus, scaled up beyond anything nature has any business doing. Right now, inside your fingernail, there are billions upon billions of tiny specks of matter at exactly that density, and they are the only reason your fingernail has any weight at all. You are already made of neutron star stuff. It's just been generously spaced out, and given room, and allowed to arrange itself into chemistry and cells, and a person who wonders about it. A neutron star is what your own material looks like, with the roominess withdrawn. That rule is doing more work in your life tonight than almost anything else in physics. Imagine for a second that it was switched off. Imagine electrons were allowed to share, allowed to pile into the same lowest state, together the way water molecules pile into the bottom of a glass. Everything would fall in. Every atom in your body would shrink toward its own nucleus, and so would every atom in the bed, the house, the ground, the planet. Chemistry needs electrons to be arranged in shells at different distances, and they are only arranged that way because the lower places are already taken. The whole periodic table, every element that differs from every other element, exists because electrons have to queue. Take away the queue, and there is no oxygen that behaves differently from carbon. No water, no salt, no protein, no you. The volume of the world is not a property of its material. It's a property of a rule about sharing. The snow is not made of snow. The snow is mostly the distance the snow keeps from itself, and it works everywhere, all the time, without exception, which is why we can say with real confidence what happens at pressures we will never produce. The rule doesn't get tired. It doesn't relax at high temperature or bend under load. It's the same rule in the tip of your finger and in the middle of a collapsing star, and the only difference is how hard something is leaning on it. And there is one fact about these objects that is harder to believe than everything else put together. A neutron, on its own, is not a stable thing. Take one out of a nucleus, set it loose in an empty room, and it will fall apart. On average, it lasts about a quarter of an hour before it comes to pieces and turns into a proton, an electron, and one of those little ghost particles from earlier. That is not a rare or delicate process. It is what free neutrons do, reliably, every time. You cannot store them, you cannot make a jar of them and put it on a shelf, because in an afternoon your jar would be full of hydrogen. So how, exactly, do you build a star out of them? How do you take a particle that cannot survive 15 minutes alone and make an object out of it that will still be sitting there in 100 trillion years? The answer is one of the loveliest pieces of reasoning in all of physics. and it comes straight back to the queue. A neutron falls apart by producing an electron. That electron has to go somewhere. It has to occupy some available state. And inside a neutron star, every available low-energy state for electrons is already full, packed to the brim by the electrons that got shoved in there during the collapse. There is nowhere for a new electron to be. And a process that has nowhere to put its products cannot happen. So the neutron sits there, wanting to decay, entirely capable of decaying, unable to decay, because the room is full. So the neutron star is made of a particle that cannot exist on its own, held together by the fact that there are too many of them. Any one of them, taken out and set down somewhere quiet, would be gone inside of an evening. All of them together, crushed into a ball 20 kilometers wide, will outlast the stars. The crowd is the reason the crowd survives. And if you could somehow remove a spoonful, the moment the pressure came off, that trapped decay would let go all at once, and the spoonful would tear itself apart in a burst of new protons and electrons, which is another reason the teaspoon on your nightstand was never going to sit there quietly. It isn't quite pure neutrons, incidentally, and the impurity turns out to matter enormously. A small fraction, somewhere around 5 to 10%, remains as protons and the electrons that go with them, and that balance is set by exactly this tug of war. Neutrons want to decay, so they push the mixture toward protons. The full electron states push back. Where those two effects meet is where the composition settles, and it settles differently at different depths. That leftover handful of protons is what makes the interior a superconductor. It's what shapes the star's magnetic field, and if the proton fraction climbs past a certain threshold, a whole extra channel of cooling switches on, and the star sheds its heat far faster, which means that from here, thousands of light years away, measuring how quickly a neutron star cools tells you the ratio of protons to neutrons inside a place nobody will ever visit. So we've reached the point where the object stops being a big heavy thing and becomes something more interesting. It's a place where the ordinary rules of matter are all still in force, every last one of them, but pushed so hard that they produce results none of us would have guessed. Nothing new has been invented. Everything has simply been asked to try harder than it has ever been asked anywhere else. It is still the armful of snow. It has only been pressed by something with no hands, no hurry, and nowhere else in the world to be. And with all of that in mind, let's go and stand on one. Not really, obviously, but let's walk toward it and see how far we get, because the walk itself tells you everything. Start with the gravity. On the surface of a neutron star, gravity pulls something like 200 billion times harder than it does in your bedroom. Numbers that size mean nothing, so here it is another way. If you took the gentlest thing you own, a feather, and let go of it a meter above that surface, it would arrive traveling faster than any spacecraft humanity has built, in a small fraction of a second. Nothing that we would call an object could exist there. A person would not fall onto a neutron star. A person would become a very thin, very fast, very brief coat of paint. You cannot stand on it. You cannot land on it. There is no version of this where anyone touches one and remains a noun. Try something softer and it stays true. Take the gentlest thing in your kitchen and drop it. One marshmallow, a few grams, released from far above, and allowed to fall through the dark. By the time it reaches the surface, it's moving at better than half the speed of light, and it arrives carrying roughly as much energy as a decent-sized city uses in electricity in a day. A marshmallow. That's what a gravity well like this does to things that wander into it. It doesn't crush things so much as it turns their falling into fire, and that same steepness works in the other direction. Because to leave the surface, to throw a ball up and have it never come back, you'd have to throw it at more than half the speed of light. Anything less, and the ball returns. Immediately, which is why the landscape there is so unbelievably flat. On Earth, mountains grow until the rock at the bottom can't bear the weight and starts to flow, which is why our tallest peaks sit at around 9 kilometers and no higher. Now imagine that same balance with the strongest material in the universe underneath, and 200 billion times the pull on top. Neutron stars do have mountains. They have bumps and ridges and features, but the tallest of them stand a few millimeters high, and the most recent modeling says even that may be generous, that the true limit could be a fraction of a millimeter. So picture it. An object 20 kilometers across whose entire surface topography is smaller than the raised print on a coin. It is smoother than anything humans have ever manufactured, smoother than the best mirrors we can polish, smoother than a ball bearing, smoother than the skin of ice on a pail left out overnight, and it got that way without anyone touching it. And then there's what the light does. Gravity that intense bends light noticeably, and near a neutron star the bending is so severe that rays from the far side curl around the edges and arrive at your eye anyway. If you were somehow floating out there looking at one, you would not see half of it, the way you see half of a ball. You'd see something like 3/4 of the entire surface at once, the far side smeared around the rim, the horizon bending up toward you instead of away, so the whole object would look less like a sphere and more like a bowl offering itself. Any place you tried to stand would seem to sit at the bottom of a shallow basin, with the ground rising gently in every direction, no matter which way you turned, like a field of snow that has quietly curved itself up around you while you weren't looking. Time bends there too, and it bends further than it does anywhere a person could ever stand. Gravity slows clocks. It's small on Earth, so small that your head ages a few billionths of a second per year faster than your feet, which is true and measured and completely useless in daily life. On the surface of a neutron star, it's not small at all. A clock there ticks about a fifth slower than a clock far away. Spend a year on that surface and you'd come back to find everyone else had lived a year and nearly 3 months. The light leaving the surface climbs out of the gravity well exhausted, stretched to redder colors, and arrives to us slightly slower and slightly softer than it left. Every neutron star we look at is showing us a version of itself running behind. Even the air there, if you can call it that, is unlike anything. Neutron stars have atmospheres, and they are about 1 centimeter thick. 1 centimeter. A layer of plasma, mostly hydrogen or carbon, at a temperature of hundreds of thousands or millions of degrees, held down so hard that it can't rise any further, spread out over that city-sized ball like the finest possible dust on a polished floor. And beneath that centimeter of atmosphere, you reach the surface itself. And the surface is where this object stops being merely extreme and starts being genuinely strange, because the crust of a neutron star is made of something that exists nowhere else in the universe. And physicists gave it a name straight out of a kitchen. The outer part of the crust is, of all things, a metal, a crystal, more precisely, a perfectly ordered lattice of iron and nickel nuclei, sitting in fixed positions with a sea of electrons flowing freely between them, which is exactly what a metal is. It is a crystal in the way the frost on a cold window is a crystal, only with not one flaw in it anywhere. So the outside of a neutron star is a single crystal of iron hundreds of meters thick, unbroken, with no grain boundaries and no flaws, because nothing in the universe is strong enough to introduce a flaw into it. If you could hold a piece, it would be the most perfect metal ever formed. And as you sink through that crystal, the pressure climbs, and the nuclei get pushed closer, and they start to swell with extra neutrons because the electrons around them keep being crushed into their protons. The nuclei become bloated, neutron-heavy versions of themselves that could never exist for a fraction of a second on Earth. So what is that crust actually made of, further down, where nothing we have names for could survive? You reach a depth where the nuclei can't hold anymore, and the neutrons start to leak out. Physicists call it the neutron drip, which is a rather lovely name for the moment. Matter gives up its last privacy. The snow is gone by then. What's left is the water that was hiding inside it, and then not even that. Below that line, you are no longer in a place made of atoms sitting in a lattice. You're in a place made of nuclei floating in a rising ocean of loose neutrons. And as you go deeper, still the ocean rises and the nuclei get closer together. And now something happens that nobody predicted from first principles and everybody loves. Two forces are arguing down there. The strong nuclear force wants nuclear matter to clump together, and electrical repulsion between all those protons wants it to spread apart. And normally the clumping wins easily, and you get little round nuclei. But at these pressures, the two are nearly matched. And when two opposite tendencies balance almost perfectly, matter stops making spheres and starts making shapes, the way frost on a cold window stops making dots and starts making ferns. First, the nuclei stay round but crowd together like dumplings in a stew. Then they merge into long rods. Then the rods flatten and join into sheets, layer upon layer of nuclear matter stacked like pages. Then the sheets fuse, and the empty space becomes the shapes instead. Tubes of nothing running through solid nuclear material, and then bubbles of nothing. And then the last of the emptiness closes, and you're through into the core. It's the snowball again, at the very end of the pressing, when there's nothing left in it to give. The physicists who worked all this out looked at their own diagrams, saw dumplings and rods and stacked sheets and tubes, and named the whole sequence nuclear pasta. There's gnocchi. There's spaghetti. There's lasagna. And there's a stage they genuinely call bucatini, after the tube-shaped kind. The name stuck. And there is something kind about it, that the strangest material in existence ended up carrying the warmest words anyone could have given it. Somebody was thinking about dinner, in a room with a whiteboard, on an evening when the sums were going well. Nobody has ever seen it. Nobody ever will. It exists in a layer a few hundred meters thick, buried under most of a kilometer of crust, on objects we can only detect as flickers of radio noise. And we know its shape because the mathematics leaves no other option. And it is the strongest material in the universe, not by a little. When it was finally simulated properly, on machines running for millions of hours, the answer came out at roughly 10 billion times the strength of steel. 10 billion. If you had a bar of it, and if it could survive being taken out, which it absolutely could not, you could hang the weight of a mountain range from it, and it would not deform. That is the flaw beneath the crust of a neutron star. And it explains the millimeter mountains. And it explains why these objects can spin as fast as they do without flying apart. And it sets up the one piece of drama that a neutron star still has left in it. Because a spinning neutron star is very slightly flattened at its poles, the way any spinning thing is, and as the years pass, it spins a little more slowly, so the amount of flattening it wants has to decrease. Something the size of a city, sheathed in the strongest crystal in the universe, needs to become a very slightly rounder ball. It can't just flow into the new shape, it has to break. So it holds, and the stress builds and holds, and eventually the crust cracks and settles, and the whole surface shifts by perhaps a millimeter. A millimeter. On a body heavier than the sun, with the strongest material in existence letting go all at once. The energy released in that one small settling can be more than our sun puts out in years. We can watch it happen from here, which still seems unreasonable to me. Certain neutron stars keep such precise time that when they stumble, the stumble is obvious. One of them, in the southern sky, does it roughly every 2 or 3 years without fail. It has been ticking away for decades, losing speed at a perfectly predictable rate. And then one day, without warning, it speeds up, just slightly. A few parts in a million. Then it resumes its slow decline as though nothing happened, until the next time. Astronomers call these events glitches, and there are thousands of them recorded now, and every single one is a message from inside a star. and the message is stranger than the stumble. The reason the star can suddenly speed up is that the inside of it is not attached to the outside. Beneath that crust is an ocean of neutrons, and that ocean is a superfluid, which means it has no viscosity whatsoever. None. Not a little. Not almost none. Exactly none. And a fluid with no viscosity doesn't behave like any liquid you've handled, because friction is the thing that makes liquids sensible. It cannot slow down. Set it swirling and it swirls forever. It will creep up the walls of its container in a film 1 atom thick and climb out over the rim. It will flow through gaps, so fine that ordinary matter can't pass. It is a liquid that has forgotten how to stop. We do have superfluids on Earth, in a handful of laboratories, made of helium cooled to within a couple of degrees of absolute zero, and watching one is a genuinely uncanny experience because it looks like a normal, clear liquid doing impossible things very calmly. What's remarkable about the neutron star version is the temperature. That interior sits at hundreds of millions of degrees, and it's superfluid anyway, because what matters isn't the temperature in ordinary terms, but the temperature compared to the enormous energies the particles already have. By its own standards, that blazing interior is bitterly cold, and so it settles into the same frictionless state that helium finds a whisker above absolute zero. A superfluid can't spin the way ordinary things spin either. It isn't allowed to rotate smoothly as one body. Instead, all the rotation has to be bundled into countless tiny whirlpools, each carrying exactly the same fixed amount of turning, no more and no less, arranged in a neat array like the holes in a colander. A neutron star's interior holds something like 1 billion of these vortices, and they get caught. They snag on the underside of the crust and stay pinned there, unable to move outward as the star slows. So the inside keeps spinning faster than the outside for years while the tension builds. Then, all at once, a great swarm of them tears free and hands their momentum to the crust, and the star jumps forward. That's the glitch. That's what we're seeing when the ticking stumbles. We are, from thousands of light years away, watching whirlpools come unstuck inside a dead star by timing a radio blip. And beneath even that, at the very center, we honestly do not know what is going on. That's not modesty, it's the actual state of the field. The pressure at the core of a neutron star is higher than anywhere else in the present-day universe, higher than the middle of the largest star, higher than anything achievable in any laboratory we could build, and matter under that kind of pressure may do things it does nowhere else. It may make heavier cousins of the neutron that only exist for fractions of a second on Earth. It may make a strange condensate of particles that ordinarily can't sit still. Or the neutrons themselves may dissolve, the quarks inside them breaking free of the little prisons they have been kept in since the universe was a second old, forming a free-flowing quark liquid that has existed nowhere in nature for 13 billion years. Quarks have not been seen loose since the first moments after the beginning. The force that binds them gets stronger the further apart you pull them, which is why nobody has ever isolated one and nobody ever will. But push them close enough together, past the point where each quark can tell which neutron it belongs to, and they may simply stop belonging to anything. If that's happening, then the centers of these objects are small preserved pockets of the newborn universe, still in the state everything was in before there were protons, sitting quietly inside city-sized balls scattered through the galaxy. Right now, tonight, while you lie there in the warm and think about it. So how do you look inside, something you cannot visit, cannot sample, and cannot see the middle of? You watch the outside very, very carefully. A telescope mounted on the space station stares at neutron stars and times the arrival of individual X-ray photons to within 100 nanoseconds, building up a picture of the hot patches on the surface as they swing past. From the way the light rises and falls, and the way the star's own gravity bends that light on its way to us, you can work out the size of the star. Match a size to a mass and you have a data point about how squeezable this matter is. Enough data points and you have the answer to what's in the middle. It's a bit like weighing a sealed box, shaking it and deducing the contents. Except the box is a dead star. And the contents are a question physics has been asking since before anyone knew such stars existed at all. And when that method was finally turned on the nearest suitable target, it produced a result nobody had ordered. For 50 years, the working picture of a pulsar had been a simple one, a ball with a magnetic field shaped like the field of a bar magnet, north at one end, south at the other, two hot patches sitting neatly at opposite poles where the charged particles come raining down. Every textbook diagram looked like that. It's what you'd draw if someone asked you to draw one. The way a child draws a magnet with the iron filings combing themselves into two neat wings on the kitchen table. It's what the beams and the pulses seem to require. The measurements said otherwise. When the X-ray arrival times were unfolded into a map of the surface, the hot patches were not at opposite poles at all. On the first star mapped this way, both of them appeared to be in the same hemisphere, one small and roundish, one drawn out into a long crescent curving across the surface like a smile. On the next, the pattern was different again, and not much tidier, which means the magnetic field of a neutron star is not a bar magnet. It's something more tangled and more individual, with loops and offsets and features we have no map for. And after 6 decades of study, the basic geometry of the thing turned out to be a surprise. The same measurements did something else quietly wonderful, which is that they saw the light bending. To fit the data at all, the models had to include the fact that the star's gravity curves the paths of its own photons, wrapping the far side into view. If you leave that out, the shape of the flicker is wrong. So, the bending isn't a calculation anymore, or an illustration in a book. It's a term in a fit to real data, without which the numbers don't work. And out of all that came the measurement everyone actually wanted. The heaviest well-measured neutron star known, an object holding about 2 1/10 times the mass of the Sun, was found to be around 25 kilometers across, which is a little wider than the lighter ones and a great deal wider than some models had predicted. That sounds like a footnote. It isn't. It means the matter down there resists being squeezed more stubbornly than several respectable theories expected, and it quietly rules some of them out. We are, from thousands of light years away, weighing and measuring the inside of a substance that cannot be brought here, cannot be made here, and cannot be seen. And we're doing it by timing flickers. Let's take one slow imaginary trip out there before we go any further, because we've been describing this object in pieces, and it's worth seeing the whole of it once, at your own pace, with nothing at all to work out. Nobody is ever going to make this journey. That's part of what makes it a good one to make lying down, in the warm, with the light off and the night doing its usual work outside the window. Start 1,000,000 kilometers away, which is about 3 times as far as the moon is from your window tonight. From here, there is nothing to see. Genuinely nothing. You could look directly at it and your eye would find only the ordinary star field behind it, because a 20-kilometer object at 1,000,000 kilometers is far smaller than anything an eye resolves, and its light, though fierce, is coming out mostly in X-rays that human eyes were never built for. If you had an instrument sensitive to those, you'd see a small hard point, hotter than any furnace, sitting there quietly. To you, floating and looking, the most remarkable object in the universe is invisible. What you would notice, if the star were one of the beaming kind, is a rhythm. Not with your eyes, with everything else. Every fraction of a second, a sheet of radio energy and high-energy particles sweeps across your position, like the beam of a lighthouse crossing a boat. And every time it does, every wire and every circuit around you registers a tick. In the total silence of that place, a pulse arrives on schedule and arrives again and again with a regularity that nothing built by hands quite matches. That's what came out of the chart paper in that field. This, out here, is what was making it. Come closer. At 100,000 kilometers, the point becomes brighter, but no bigger. At 10,000, still a point, but now the gravity has become a presence rather than a fact. You are being pulled forward hard. And more importantly, you are being pulled unevenly. Because the end of you nearest the star is closer than the end of you furthest away, and gravity this steep does not treat the two the same. You would feel yourself lengthening. Gently at first, the way you feel a lift start to move, and then not gently. At 1,000 kilometers, it finally shows itself as a disk. And the disk is not what you expect. It has a hard edge. Stars don't have hard edges. Every star you have ever seen is a ball of glowing gas that fades at the rim, thins out, has an atmosphere going soft into space. This thing has an edge, like a coin, sharp and definite, because its atmosphere is a centimeter thick, and there is nothing between the surface and the vacuum. It is the only star-sized object in the universe that looks manufactured. At 100 kilometers, the geometry gives up. The star is now filling a huge part of your view, and the light coming from it is arriving along curved paths, so you are seeing around the edges of it, seeing terrain that ought to be hidden on the far side, wrapped up over the rim toward you. The horizon, instead of falling away, rises. The surface seems to curl upward in every direction, like the inside of a bowl you are being lowered into. And behind you, the rest of the universe, every galaxy and every star that isn't this one, is being squeezed by the same bending into a shrinking bright circle overhead, as though the whole of creation were retreating up a well shaft. And time is coming apart between you and home. Your watch is running slower than every watch anywhere else, and you would not feel it, because feeling requires comparison and everything local. Your thoughts, your pulse, your breathing is slowing by exactly the same fraction. Only the outside world would give it away. If someone had stayed behind and was sending you a signal once a second, the signals would arrive faster and faster, bluer and bluer, the world outside rushing on while you seem to yourself to be perfectly ordinary. And then, of course, the trip ends, because nothing that is made of anything can arrive at that surface. There's no gentle version. Long before you got there, you'd have been drawn out into a thread and then into a fine spray, and the spray would land at better than half the speed of light and add its small warmth to a crust that has been cooling for 1,000,000 years. That's the honest end of the thought experiment, and I don't tell it to unsettle you, because you're not going and neither is anyone else. I tell it because it's the reason we know these objects only from a distance, and always will. And there is something restful in that. There are places in the universe that will never be visited by anything, never surveyed, never landed on, never photographed from close up by any instrument any civilization could build. They will simply keep spinning, unobserved and undisturbed, above every roof and every sleeping town, for a length of time that has no useful comparison, which makes it all the more remarkable that we know as much as we do. Everything we have learned about these objects, every number I've given you tonight, the density and the crust and the millimeter mountains and the frictionless ocean and the pasta, has been worked out from a long way off, by people watching very faint things very patiently and thinking very carefully about what could possibly explain them. Nobody has taken a sample, nobody has flown past one. All of it came from light, arriving after a long journey, at instruments on and around one small warm planet, and from the willingness of a few people to take an oddity seriously instead of writing it off. Somebody guessed all of this a long time before there was any way to look, not the details, but the thing itself, the existence of a star made of neutrons. And they guessed it before there was the faintest hope of ever seeing one. The neutron was discovered in 1932 in a laboratory in England, and it was a proper surprise. Until then, the picture of the atom had protons and electrons and a nagging sense that the arithmetic didn't add up. And then along came this heavy, neutral, entirely new resident of the nucleus. 2 years later, 2 astronomers working in California published a short note, barely more than an abstract, in which they suggested that the enormous stellar explosions they had started calling supernovae might be the moment an ordinary star turns into a star made almost entirely of neutrons. Set those dates beside one another. The neutron had been known for 24 months. Nobody had worked out how stars shine. Nobody had a computer. And these two looked at a brand new particle and at the brightest events in the sky and connected them with a line that turned out to be exactly right. One of the two, a Swiss astronomer with a legendary temper and an even more legendary ability to be correct, would also coin the word supernova and would go on the following year to notice that galaxies in clusters were moving far too fast for the visible matter to hold them together, which is the first sighting of dark matter. He was ignored on that for about 40 years too. Some people are simply early. A few other people were circling the same idea at the same time, which is usually how these things go. A young Russian theorist had wondered, in the same year the neutron was found, whether stars might have cores made of one enormous nucleus, which is not quite the right answer, but is standing in exactly the right place. And toward the end of that decade, two physicists in California sat down and did the sum properly for the first time. If you have a ball of neutrons held up by nothing but their refusal to share, how heavy can you make it before the refusal fails? They cranked through the equations by hand and got an answer of about 7/10 of the mass of the Sun, which is too low because they had left out the way neutrons push against each other at very short range, and nobody at the time knew enough about that force to include it. But the shape of the answer was right, and it was the first time anyone had written down the idea that there is a weight above which nothing at all can hold. One of those two then asked the obvious follow-up question, which is what happens to a star that goes over the limit, and wrote a short paper concluding that it would simply keep contracting, closing itself off from the rest of the universe, cutting its own light off from anyone watching. That is the first serious description of a black hole in the physics literature, and it is one of the most important papers of the century, and it appeared on the 1st of September, 1939, which is to say it was published on the morning the Second World War began in Europe. Nobody read it. The author spent the following years on other work entirely, and the idea sat untouched for the better part of 25 years before anyone picked it up again. So, the full picture, the neutron star, and the limit above it, and the thing that lies beyond the limit, was essentially complete before 1940. It was written down by a handful of people in a few pages, using pencil and paper, about objects that could not be seen, on the strength of a particle that had been known for less time than a university degree takes. And then the world had other business, and the whole subject went quiet. And then, for a third of a century, nothing. Their neutron star sat in the literature as a curiosity, a thing that might exist, but could never be checked. Because how would you check it? 20 kilometers across, in a galaxy 100,000 light-years wide. You could put one anywhere in the sky, and no telescope ever built would show you a dot. It was, as far as anyone could see, a permanently untestable idea. The theorists moved on. Occasionally somebody would write a paper working out how hot such a thing would be, or how fast it might spin, and the papers would be filed and forgotten. Now, come forward to a muddy field outside Cambridge in the summer of 1967. There's a new radio telescope there, and it is not a dish. It's 4.5 acres of wooden posts and wire, more than 1,000 posts, 2,048 aerials, over 100 miles of cable, and a great deal of it was built by hand by the graduate student who would go on to run it. Her name was Jocelyn Bell. She was 24, and the instrument was designed to look for the twinkling of distant radio sources, which meant it produced its readings not on a screen but as ink on a moving roll of paper. Close to 100 feet of chart paper a day, and her job, every day, was to unroll that paper by lamplight and read the whole of it with her eyes. By the end of the survey she had gone through miles of it, and somewhere, in that endless scribble, she noticed a thing she later described as a bit of scruff. Not a signal, not a spike, just a quarter of an inch of untidiness in 400 feet of otherwise ordinary ink, in a spot on the sky where nothing interesting was supposed to be. Anyone else would have marked it as interference and moved on. Radio astronomy is full of interference. Cars, thermostats, radar, a badly suppressed motorbike 2 fields over. She had a very good memory for the shape of her own charts, and she remembered having seen that same scruff before, in the same place. And that was the thing that snagged her, so she checked when it appeared, and it kept appearing 4 minutes earlier each day. That detail is the whole story, and it's beautiful, because 4 minutes a day is exactly how the stars run ahead of our clocks. Anything on Earth keeps Earth time. Anything in the sky keeps star time. Whatever was making that scruff was not a motorbike. It was out there. She had the recorder run faster to spread the scruff out and see what it was made of, and after weeks of trying, on a cold night in November, the pen finally drew it properly. A series of sharp pulses, evenly spaced, 1 every 1 1/3 seconds, as regular as anything that had ever been recorded from the sky. And nobody knew what could do that. Nothing natural was supposed to be able to keep time like that. So for a few weeks, cautiously and slightly awkwardly, the possibility on the table was that somebody was calling. They labelled the source with a little joke that was also a real hypothesis. Little Green Men, number 1. Belle has said, since that she was mostly annoyed, she had a thesis to finish. And here was some alien civilization messing up her data. What settled it was that she went looking and found a second one in a completely different part of the sky, ticking at a completely different rate. 2 separate civilizations, both broadcasting at the same wavelength, both aimed at one field in England, was not a story anyone could sell. It was nature. Something out there was ticking. Within weeks, the answer arrived from the theorists. And it was the 33-year-old idea nobody could test. A neutron star, spinning, dragging a magnetic field around with it, throwing a beam of radio waves out into space like a lighthouse. The paper announcing the discovery came out in early 1968. The name pulsar was not coined by any of the scientists, incidentally, but by a newspaper journalist writing it up for a London paper, who squashed pulsating and star together and gave the objects the name they'll keep forever. There's a shadow on the story, and it's worth telling straight. When the Nobel Prize was given for the discovery, in 1974, it went to Bell's supervisor and to the head of the group, and not to the person who spotted the scruff, kept the charts, chased the 4 minutes, and sat up through the cold nights in a hut at the edge of a wet field to catch the pulses. It caused an argument at the time, and it has never entirely gone away. Her own response, across 5 decades of being asked about it, has been consistently gracious. And she has said more than once that awards are much more fun than prizes, and that she has had a wonderful life. In 2018, she was given a very large physics prize of her own, $3 million, and she gave away every single penny of it to fund graduate scholarships for students from backgrounds that physics has historically overlooked. She said she didn't need the money. It's the best possible ending to that particular story. And it means that somewhere right now, there are young physicists studying on a fund built entirely out of a 1/4 inch of scruff, on a roll of paper, in a cold hut, at the edge of a field, on a night nobody expected anything from. So why does a dead star spin at all, let alone spin fast enough to be mistaken for a message? For the same reason a figure skater speeds up when she pulls her arms in. Spin is conserved. Not the rate of spin, the total amount of turning, and if you shrink the thing that's turning, the rate has to climb to keep the books balanced. Our sun is a slow, dignified rotator. It turns once about every 25 days at its equator, which for a ball 1.5 million kilometers across is a stately pace. Now collapse that ball to 20 kilometers, keeping the turning it already had, and pull the skater's arms in by a factor of 70,000. The answer comes out in the hundreds of revolutions per second. The same squeeze happens to the star's magnetic field. Every star has one, threading through it, held in the moving charged gas, and when the core collapses, those magnetic field lines are dragged in and crowded together into a fraction of the space. A field that was ordinary and gentle across 1,000,000 kilometers gets crowded into a space 70,000 times smaller and comes out something like 1,000,000,000 times stronger. And it does not, in general, line up with the axis the star is spinning on, any more than Earth's magnetic north sits neatly on the geographic pole. So you get a lopsided arrangement, a colossal magnet whipping around hundreds of times a second, tilted, flinging charged particles off its poles in two narrow beams that sweep the sky like the light from a lighthouse on a headland, which is why we don't see most of them. A lighthouse only helps if you happen to be in the water it points at. If the beams of a given neutron star never sweep across our little corner of the galaxy, that star is completely invisible to us, no matter how bright the beams are. Every pulsar in every catalogue is simply one whose lighthouse happens to include our address on its rounds. Somewhere between 1/5 and 1/10 of them do. The rest are out there ticking away for nobody, or rather for whoever else in the galaxy happens to lie along the sweep, keeping perfect time in a direction we will never occupy. There's a boundary around every one of them, and it's one of the quietest ideas in the subject. A neutron star's magnetic field is locked to the star, so it turns with it, like the spokes of a wheel. And the further out along a spoke you go, the faster that part of the spoke has to sweep, which means there is a distance at which the field lines would have to be moving at the speed of light in order to keep up, and beyond that distance they simply cannot. They break open and stream away instead. Physicists call that boundary the light cylinder, and it is the edge of the star's real territory, the surface where being attached stops being possible. For a slow old pulsar turning once a second, the light cylinder sits about 48,000 kilometers out, a comfortable ring around the star, further away than most satellites orbit our planet. For the record holder spinning 716 times a second, it closes right in. Its light cylinder is only about 67 kilometers from the surface. So that star's entire magnetic estate, everything it can hold on to, is a bubble smaller than the distance you might drive to visit family, wrapped around a ball 20 kilometers wide, and outside that bubble, the field lines are torn open and flung into space. That tearing is where the light comes from. Charged particles get ripped off the surface at the magnetic poles, accelerated along the open field lines by voltages beyond anything a human machine has produced, and hurled outward at very nearly the speed of light. On the way they radiate, and the radiation makes new pairs of particles, and those get accelerated too, so a cascade builds up in the space above each pole and pours out into the two beams that sweep the sky. And here's the honest bit. After nearly 60 years of study, thousands of these objects catalogued, and some of the finest theorists in physics working on the problem, nobody knows exactly how the radio beam is produced. The general picture is solid. The particles, the acceleration, the cascade, all of that stands. But the radio waves come out coherently, with the particles somehow radiating in step with each other, like a choir rather than a crowd. And that coherence is enormously more powerful than the sum of the individual voices, and the mechanism that organizes it has never been pinned down. The very first thing we ever noticed about these objects, the ticking on the chart paper, the thing that started all of it, is still not fully explained. There's something restful in that. A field that has answered so many enormous questions still cannot say exactly how the ticking gets made. It is the sound in the house at night that nobody can quite place. One of them we can date exactly, which is rare and rather wonderful. In the summer of 1054, a new star appeared in the constellation we call Taurus. Court astronomers in China recorded it carefully, and there are notes from Japan and the Arab world and possibly a rock painting in the American Southwest. It was bright enough to be seen in broad daylight for 23 days, and visible at night for nearly 2 years, and then it faded, and the sky closed over it. Point a modern telescope at that spot now, and you find a beautiful ragged cloud of glowing gas, still visibly flying outward. And at the heart of the cloud, a neutron star, spinning 30 times every second, throwing its beam across us 30 times a second, which it has done without missing a beat since the year people looked up and wrote down what they saw. We can watch it slowing. It loses about 38 billionths of a second per day, every day, reliably. 1,000 years of watching a star run down, and it has barely begun, and 30 times a second is nothing. The record holder, buried in a dense cluster of stars near the middle of the galaxy, spins 716 times every second. 716 full rotations of a city-sized object heavier than the sun in the time it takes you to say the word. The material at its equator is moving at close to a fifth of the speed of light. If you could somehow hover above it, you would not see it turning. You would see nothing at all, because nothing that fast leaves an impression on an eye. And if it made a sound in some imaginary air, it would be a low, steady hum, 716 cycles per second, which is very nearly a high F above middle C. There is a dead star near the center of our galaxy humming a note you could sing. It wasn't born that fast, which is the last twist of the spin story. Young pulsars are born spinning quickly, and then slow steadily for millions of years until they cross a threshold, the point at which they can no longer generate the beams, and they go quiet. The galaxy is full of these silent ones, but if a dead, quiet pulsar happens to have a companion star nearby, and if that companion swells in old age until its outer layers begin falling toward the neutron star, then all that infalling matter spirals in and hands over its motion, spinning the old corpse back up over hundreds of millions of years. Astronomers call these recycled pulsars, and they are old stars given a second, faster, far more precise life by the death of the star beside them. And that feeding is worth watching in its own right, because it produced the other great accidental discovery of this story, 5 years before the scruff on the chart paper. In the summer of 1962, a small rocket went up from a desert range in New Mexico carrying X-ray detectors. It had about 5 minutes above the atmosphere before it fell back. And the plan was modest, to see whether the moon glowed in X-rays when the sun shone on it. It did not find the moon. What it found, in those few minutes, was a source in the direction of the constellation Scorpius blazing so brightly in X-rays that the team assumed at first that something had gone wrong with the equipment. Nothing had gone wrong. They had stumbled onto the brightest X-ray object in the whole sky apart from the sun itself, sitting there in a patch of the night that had looked, to every eye and every telescope before them, completely ordinary. Nobody had the slightest idea what it was. It took years to work out, and the answer is a neutron star with a companion. If a neutron star has an ordinary star close enough beside it, and if that star swells in old age until its outer layers feel the neutron star's pull more strongly than their own, gas begins to leave the living star and fall toward the dead one. It doesn't fall straight in. Everything in orbit has sideways motion, so the gas spirals, forming a flat disk that circles the neutron star and slowly grinds inward, each ring rubbing against the ring beside it. That rubbing heats the disk, and near the middle, where the gas is moving at a serious fraction of the speed of light, the temperature reaches many millions of degrees, and matter that hot does not glow red or white. It glows in X-rays. The efficiency of this is the part that stops physicists in their tracks. When hydrogen fuses into helium in the heart of a star, the process converts about 0.7% of the mass into energy, and that fraction is what powers every star in the sky for billions of years. Drop that same hydrogen onto the surface of a neutron star instead, and simply falling releases something like 10 or 20% of its mass as energy. Falling beats fusion by a factor of 20 or more. Gravity, given a steep enough hill, is a far better engine than the nuclear furnace inside the sun, and these accreting systems are the most efficient power sources in nature short of a black hole. Then it gets better, because the fuel piles up. The gas arriving from the companion spreads out over the surface and gets crushed under its own weight into a layer, and that layer is hydrogen and helium under the most intense pressure available anywhere. For a few hours it holds. It gets hotter and denser, and closer to the point of ignition, and then, somewhere in that ocean, one patch tips over the edge, and the burning spreads across the entire surface of the star in less than a second. The whole skin of the object ignites at once. The star flares to hundreds of times its usual brightness for a few tens of seconds, and then fades, and then the gas starts piling up again, and a few hours later it happens once more. We have watched some of these systems do this thousands of times. Thermonuclear flashes, on a fixed schedule, across the entire surface of an object the size of a city, powered by a layer of fuel a few meters deep. And underneath, occasionally, something even slower is happening. The ash from all that burning, mostly carbon, sinks down and accumulates over months, until it too reaches its own ignition point and detonates in a burst that lasts not seconds but hours, releasing in one event as much energy as 1,000 of the ordinary flashes. Those deeper events happen roughly once a year in a given system, and they burn through a layer buried tens of meters under the surface, which means that when we see one, we're watching the star's cellar catch light. So the same object we've been calling a corpse turns out to have an atmosphere, an ocean, weather, seasons of a sort, a fuel supply, and a routine. It has a place where the burning happens and a place where the ash collects. And every one of these things was worked out by people looking at nothing more than the brightness of an X-ray source rising and falling, from a distance so great that the star itself is, and always will be, a single unresolvable dot. So, what do you do with a corpse that will not stop ticking? You use it. A recycled pulsar keeps time better than almost anything human beings have built. That's not a figure of speech. Take one of the best of them. Watch it for 10 years, and the arrival of its pulses can be predicted to within a few hundred billionths of a second. Over that kind of stretch, it holds its own against the atomic clocks in national laboratories, the ones kept in temperature-controlled rooms by people whose entire job is to keep them steady. This one is a corpse. It sits in vacuum, unattended, at a temperature of 1,000,000 degrees, having been thrown out of an explosion, and it keeps better long-term time than a machine we built on purpose, in a quiet room on a stone bench with 3 people watching it. The reason is very simple. It's a flywheel, 1.5 times the mass of the sun, spinning hundreds of times a second, packed into a ball 20 kilometers wide and sheathed in the strongest material in the universe. There is essentially nothing in the galaxy that can nudge it. A planet-sized rock could hit it, and the rate would barely notice. Gas can rain on it, magnetic fields can tug at it, and the effects are so small that we have to model them just to subtract them out. It is the most stable spinning object nature knows how to produce, and there are hundreds of millions of them, so we started using them, and the first use is still the loveliest. In the early 1970s, 2 spacecraft left Earth on paths that would carry them out of the solar system forever. And somebody had the idea of bolting a plaque to each of them, a message for anyone who might ever find them. The hard part of a message like that isn't language, it's the address. How do you tell a stranger where you live when you can't assume they share a single word, a single number, or a single reference point with you? The answer engraved on those plaques is a starburst of 14 lines radiating from a single point. And along each line, written in the simplest counting marks the universe allows, is the ticking rate of one particular pulsar, 14 dead stars, each with its own signature rhythm. Anyone who can find those 14 clocks in their own sky can work backwards to the one place all 14 lines meet, and that place is here. Our address is written in the pulse rates of things that no human being had even seen 5 years before the plaque was drawn. And the addresses work forwards as well as outwards. Pulsars slow at rates we can measure precisely. So their rhythms are not just a location, they're a date. Anyone finding that plaque a million years from now could compare the ticking rates on the metal with the ticking rates in their sky and read off when it was launched, the way you read the rings in a tree. It is the only clock we have ever made that gets more informative with age. That idea has since gone from poetry to engineering. A few years ago, an X-ray telescope on the space station ran an experiment where it ignored every navigation system on board, looked at a handful of millisecond pulsars, timed their pulses, and worked out its own position in orbit from nothing else. It got the answer to within a few kilometers, while moving at 8 kilometers per second. What that demonstrates is that a spacecraft anywhere, at Neptune, in the space between stars, with Earth long since too faint to help, could still know exactly where it was, by listening to dead stars. The galaxy came with a navigation system already installed. We just had to notice. They test our deepest theories too, and they do it better than anything on Earth. There's a pair of neutron stars out there, discovered a couple of decades ago, that orbit each other every 2.5 hours, and both of them are pulsars, both beaming, both being timed. That double system is the finest laboratory for gravity anyone has ever had access to. As the two swing around each other, they stir up ripples in space-time that carry energy away, and losing that energy makes the orbit shrink, and it shrinks by about 7 millimeters a day. 7 millimeters on an orbit a few million kilometers around. We can measure that, and the measurement agrees with what Einstein wrote down a century ago to within a fraction of a percent. Every clause of that theory that anyone has thought to test in that system has passed. 2 dead stars, closing on each other by the width of a grain of rice a day, keeping a 100-year-old promise. Here's a piece of trivia that surprises almost everybody. The first planets ever discovered outside our solar system do not orbit a sun-like star. They orbit a pulsar. In 1992, 3 years before the famous discovery of a planet around an ordinary star, 2 astronomers noticed that one particular pulsar's pulses were arriving a few thousandths of a second early, then a few thousandths late, in a repeating pattern. Something was tugging the star gently back and forth, which meant something was orbiting it. 2 planets, then 3, going round and round a dead star that had already exploded once, in a place where no life could ever have arisen or survived. We found other worlds for the first time by noticing that a corpse was wobbling, and the grandest use came only recently. Imagine you want to detect gravitational waves so long and slow that a single wave takes years to pass. Waves made by supermassive black holes circling each other in the hearts of distant galaxies. No instrument on Earth is big enough. You need a detector, light years across. So astronomers took dozens of the most reliable millisecond pulsars scattered across the sky, timed every one of them for decades, and looked for the faint pattern you would expect if space itself were gently stretching and squeezing between us and them. In 2023, 4 separate teams on 4 continents announced they had found it. The whole galaxy is humming, very quietly, at frequencies of a few billionths of a cycle per second, and we heard it by using dead stars as the arms of an instrument the size of everything. Now let me tell you about the ones that broke the scale. Most neutron stars carry magnetic fields around 1 trillion times stronger than Earth's, which is already beyond anything a person can picture. A small number carry fields 1,000 times stronger even than that. We call them magnetars, and there may be a few dozen known against thousands of ordinary pulsars, and every one of them is doing something to the space around it that has no equivalent anywhere else. The ladder of magnetism goes like this. Earth's field, the thing that turns a compass needle, is about half a Gauss. The magnet holding a photograph to your fridge is around 100. A hospital scanner, the machine that makes a room full of people take their watches off, runs at about 30,000. and it can pull a steel chair across a floor. An ordinary neutron star is 1 trillion. A magnetar is 1,000 trillion. If you brought a magnetar's field into a laboratory, it would be tens of billions of times stronger than the strongest scanner we can build. And the word field stops being useful because at that intensity, magnetism stops being something that acts on matter and starts being something that redesigns it. Atoms in that kind of field cannot stay round. The electron clouds get squeezed sideways until each atom is stretched into a long, thin needle, hundreds of times longer than it is wide. And chemistry, as we understand it, simply stops. Molecules can't form in their usual shapes. Ordinary matter would not be able to hold itself together in any arrangement you'd recognize. No water, no wood, no skin. You would not need to touch a magnetar to be undone by it. Somewhere around 1,000 kilometers away, still further than most of our satellites orbit, the field alone would pull apart the water in a human body, because water is weakly magnetic, and everything in you is made of it. There's a lovely illustration that gets quoted in the literature, which is that a magnetar could wipe the stripe on a credit card from a distance halfway to the moon. We met the first one of these without knowing what it was, and the way it was tracked down is worth telling slowly. On the 5th of March, 1979, a wave of gamma rays swept through the solar system. It crossed the Earth in the small hours, and nobody standing outside under that night sky felt a thing. There were spacecraft scattered all over the place at the time, some near Venus, some near Earth, some far out on long, lonely trajectories, and one after another they each recorded a spike so sharp that several of their detectors simply stopped working, overwhelmed. 9 of them caught it in total. And because they were spread across the solar system, and because the wave took time to cross it, the arrival times were all slightly different. A spacecraft near Venus registered it before one near Earth. Compare the timings, work backwards, and the direction the wave came from can be pinned down with real precision, the same way you can locate a lightning strike from the delay between one microphone and another. The direction pointed straight at a small bright knot of gas in a satellite galaxy of ours, a place where a star had exploded a few thousand years earlier. That should have been the end of it. Bursts of gamma rays from the sky were known. They were a mystery, and this was a very bright one. But 2 months later, the same spot did it again, and then again. And that was not supposed to happen, because the leading explanations for gamma ray bursts at the time all involved something ending. And endings do not repeat. Whatever was in there had survived its own outburst and was capable of another. A whole new category had to be invented for it, and for years it was known simply as a repeater, because that was the only thing anyone could say about it for certain. The explanation came in the early 1990s from 2 theorists who worked out what would happen if a neutron star were born spinning fast enough for the churning inside it to act like a dynamo, winding its magnetic field up far beyond the ordinary. Their answer was a star with a field 1,000 times stronger than any pulsar, so strong that the field itself would strain the crust from below, cracking it, releasing energy in exactly the bursts that had been recorded. They put the words magnetic and star together and called it a magnetar, and within a few years the observations had caught up, and the class was real. They occasionally lose their tempers, and in December of 2004, one of them did something that is still hard to hold in the mind. On the 27th of that month, a burst of gamma rays arrived at Earth from a magnetar near the center of our galaxy, roughly 50,000 light-years away, which is most of the way across everything we can call home. It lasted about 0.2 of a second. In that 1/5 of a second, it released more energy than our sun gives out in 100,000 years. It saturated the detectors on every spacecraft that happened to be facing that way, including one orbiting Mars. It measurably ionized the upper atmosphere of Earth on the night side, from 50,000 light-years away, from an object 20 kilometers across. It is the brightest thing from beyond our own solar system that human instruments have ever recorded. and almost nobody noticed, because it happened in a part of the spectrum our eyes cannot see, over a quiet week between Christmas and the New Year, while most of the planet was asleep. But the beautiful part is what came afterward. As the flare faded over the following minutes, the fading light was not smooth. It flickered, and the flickering had notes in it, steady frequencies buried in the decay. What the instruments were recording was the crust of that star vibrating, ringing, the way a struck bell rings, still shivering from the release. Some of those notes came in at 18 cycles per second, some at 92, some at 150, some at 625. Look at that list for a moment. Those are audible frequencies. Those are notes in the range of a human ear, in the range of a cello and a voice. If you had been somewhere that could carry sound, you would have heard a star ring in a register you could hum back. It is the only time we have ever caught one doing it. And from those notes, physicists have been trying to work out the stiffness of the crust ever since. The way you can tell the thickness of a wine glass by its tone. The energy for all that doesn't come from the spin either. Ordinary pulsars run on rotation, slowly trading their turning for light. And they last millions of years doing it. A magnetar runs on its own magnetic field, unwinding, the field lines twisting, snapping, rearranging, and that's a far richer and far shorter kind of life. Most magnetars go quiet within about 10,000 years, which in the life of a star is almost no time at all. And in 2020, one of them in our own galaxy did something else remarkable, which is that it produced a millisecond flash of radio energy of exactly the kind that had been arriving from distant galaxies for years without anyone knowing what made them. One of the great open mysteries in astronomy got a face that night. And the face was a magnetar. Now put two of them together, because that's where tonight has been heading all along. What happens when the two densest objects in the universe meet each other? Sometimes a pair of big stars are born as a couple, orbiting each other from the beginning, and sometimes both of them survive their own explosions without being flung apart, and what's left is two neutron stars going around one another in an empty patch of some distant galaxy. Two cities, 2 suns worth of mass, circling, and they cannot circle forever, because two heavy things swinging around each other stir the shape of space itself, sending out ripples that carry energy away, and every joule that leaves in a ripple is a joule the orbit no longer has. So they fall toward each other. Unbelievably slowly at first. A pair like that can spend hundreds of millions of years closing the gap by a few millimeters a day. But the closer they get, the harder they stir, and the harder they stir, the faster they lose, and the whole thing runs away at the end. The last day is faster than the first 100 million years. The last hour is faster than the day. In the final minutes, they are whipping around each other several times a second, then dozens of times, then hundreds. Two objects heavier than the sun orbiting hundreds of times a second at a fraction of the speed of light, and the space around them is being wrung out like a wet cloth over a sink. All of it in a patch of sky that looked, from here, completely dark and completely quiet. Then they touch, and when they touch, the tides tear both of them open, and a spray of the densest material in the universe is flung out into ordinary space where nothing is squeezing it anymore, and it comes apart. We watched this happen. In August of 2017, on an ordinary Thursday, 2 detectors in the United States and 1 in Italy recorded a signal that lasted about 100 seconds, a rising tone climbing in pitch and frequency, exactly the way theory said the last spiral of 2 neutron stars would sound if you could hear the shape of space. 1 7/10 seconds after the tone ended, a satellite recorded a short burst of gamma rays from the same patch of sky, and then the message went out. And within hours, something like 70 observatories on every continent and in orbit had swung around to look, and they found it, a new point of light in a quiet elliptical galaxy about 130 million light-years away, in a place where the night before there had been nothing at all. That night is worth slowing right down for, because there has never been another one like it. The alert went out automatically, machine to machine, within minutes. Around the world, in observatories and in kitchens and in bedrooms, thousands of phones went off at once, and a very large number of people who were doing something else entirely stopped doing it. The trouble was that the detectors could only narrow the source down to a patch of sky roughly the size of a few hundred full moons, and there are a great many galaxies in a patch that size, and the patch was setting in the southern sky within hours. So it became a race. Telescope after telescope in Chile and elsewhere swung to the region and began working through candidate galaxies one by one, looking for a dot that had not been there before. A 1-meter telescope in the Chilean mountains found it first, about 11 hours after the ripple passed through the Earth. A small new point of light on the outskirts of a quiet elliptical galaxy. Within the following day, essentially every major instrument humanity has was pointed at it on the ground and in orbit, watching in gamma rays and X-rays and ultraviolet and visible light and infrared and radio, all at once, all on the same object. That had never happened before. For the whole of history, astronomy had been the study of light. That night it became the study of light and gravity together, from a single event. And the papers that came out of it carry the names of a substantial fraction of all the astronomers alive. 2 extra gifts fell out of it, and they're the kind of thing that only comes from measuring the same event 2 ways. The first is a measurement of the universe's expansion that owes nothing to any of the old methods. Normally, working out how far away a galaxy is means climbing a ladder of assumptions. One calibration resting on another, and each rung adds uncertainty. But the shape of a gravitational wave signal tells you directly how much energy the event released, and comparing that with how loud it arrived tells you how far away it was, cleanly, with no ladder at all. Combine that distance with how fast the host galaxy is receding, and you have the expansion rate of the universe from one event, measured in a way nobody could have attempted a decade earlier, from a light that arrived one warm August night, and was gone again inside a fortnight. The second gift is smaller and quieter. The ripple in space and the flash of gamma rays left that collision at the same moment and travelled side by side for 130 million years across a distance so large that the light set out before flowering plants were common on Earth. They arrived 1 7/10 seconds apart. After 130 million years of racing, less than 2 seconds between them, and most of that gap is explained by the flash needing a moment to escape the wreckage, which tells us, with a precision no laboratory could dream of, that gravity and light travel at exactly the same speed to within about 1 part in 1,000 million. Einstein said they would. A pair of dead stars and 130 million years of patient travel through the dark delivered the proof on an August night while the world got on with its evening, and the light they were watching did something none of them had ever seen before. It started blue and faded fast, and over a few days it turned deep red, far redder than any ordinary explosion, and it stayed warm for far longer than the amount of material could possibly explain by itself. Something in that debris was generating its own heat, and the only thing that could do it was radioactive decay on an enormous scale, from elements that had been freshly made minutes earlier and were still settling down into stability. Which brings us to the thing I promised at the start. So let me back up one step to make it land. Stars build elements by fusion, and fusion works beautifully all the way up to iron and then stops, because past iron you have to put energy in rather than getting it out. So, a star, no matter how large, cannot make gold in its core. It cannot make platinum or uranium, or most of the heavy end of the periodic table. Those elements need a completely different method, and the method requires a place absolutely drowning in free neutrons, so that a nucleus can swallow one and another, faster than it can fall apart in between. climbing up the chart of the elements in a few seconds flat. And where in the universe is there a place drowning in free neutrons? There is exactly one obvious answer, and we spent the whole night walking around it. When two neutron stars tear each other open, the material that sprays out is the most neutron-rich matter in existence, suddenly free, suddenly not being crushed, and every nucleus in it starts eating neutrons as fast as it can. In a couple of seconds, that spray builds the heavy half of the periodic table. Then it flies outward as a glowing radioactive cloud, cooling, decaying, turning slowly red, which is precisely the light that all those telescopes recorded through that night in August. The estimates from that single collision came in at something like 10 times the mass of the Earth in gold and platinum alone. One event, two dead stars, in a galaxy so far away that the light left before there were people, made more precious metal than our whole planet weighs, and threw it out into space to drift and mix into gas clouds and eventually settle into new solar systems. And so, here is the payoff. The gold in a wedding ring on somebody's hand, the gold in the connectors inside the phone that might be charging next to your bed, the platinum in the exhaust of the car outside, almost certainly began in a collision of this kind. Not made in a star, made in the wreckage of two stars that had already died, touching each other at half the speed of light. Astronomers still argue about how much of it comes from mergers and how much from other rare and violent places. And the argument is a good one, but nobody doubts that a real share of the gold on Earth was assembled in a few seconds by objects like the ones we've been visiting. You have very likely held some. It is the only jewelry in the universe with that particular provenance. And this had already been going on for a very long time before there was anywhere for it to land. Our galaxy is around 13 billion years old. The Sun is 4.5. So there were 8 billion years of stars living and exploding and pairing off and colliding before our solar system was so much as a cloud, and every one of those events salted the gas of the galaxy a little more richly with the heavy end of the periodic table. By the time the cloud that became the Sun began to draw itself together, it was not fresh material. It was thoroughly seasoned. Gold, platinum, uranium, iodine, all of it already mixed in tiny quantities, from events that had happened elsewhere, long before, and had spent the intervening ages drifting. There is even a hint of a specific one. Certain very heavy radioactive isotopes decay on timescales of tens of millions of years, and the traces they leave behind in the oldest meteorites, the rocks that formed at the very beginning of the solar system and have been sitting in space ever since, can be read like a receipt. The mixture in those rocks suggests that a substantial batch of heavy elements arrived in our neighborhood not long before the Sun switched on, perhaps 100 million years before, which in the life of a galaxy is the day before yesterday. Somewhere out there, in a part of the galaxy we can no longer identify, two dead stars finished a spiral they had been in for hundreds of millions of years, and the debris drifted for a while, and it was still drifting through the neighborhood when the cloud that would become the Sun and the Earth and the water and the snow and everything you have ever touched started to collapse. So the chain runs like this, laid end to end, slowly. A star, big and blue and short-lived, burned for a few million years and collapsed in 1 second into a ball 20 kilometers across. So did another one nearby. The two of them circled each other for hundreds of millions of years, losing height by a few millimeters a day. They touched, and in about 2 seconds they built the heavy half of the periodic table and threw it outward. That material drifted, cooled, joined a cloud, and the cloud collapsed into a sun and a set of planets. On one of those planets, some of it ended up in the crust. Some of that was dug up, melted, drawn into wire and pressed into a setting. And some of that, quite possibly, is in this room with you now, warm from being worn, on a hand or on a shelf, or inside the small glowing machine you might be listening to me through. As for the two stars themselves, they didn't survive it. A merger like that leaves behind a single object too heavy for even neutrons to hold up, and it collapses through the last flaw there is and becomes a black hole, probably within a second or two, which gives you the whole ladder in one sentence. Electrons refuse until they can't, then neutrons refuse until they can't, and after that there is no third refusal. The line between the two is startlingly precise. Below about 2 and a bit times the mass of the Sun, you get a neutron star that can sit there for the rest of time. Above it, nothing in physics is stiff enough, and the object simply keeps going, which means these things live in a very narrow band of possibility, and they have families and habits like anything else. The heaviest one we know of got that way by eating. It's a small class of systems that astronomers call black widows, where a pulsar spins so fast and blows such a fierce wind of radiation that it slowly boils away the companion star feeding it, evaporating its own supply, gaining mass and destroying its source at the same time. There are gentler ones and stranger ones. There's a candidate out there that seems too light to have formed the ordinary way, so light that some people suspect it isn't neutrons in there at all, but loose quarks all the way through, a different kind of star wearing a neutron star's clothes. That idea deserves a moment of its own, because it's the strangest thought in an evening full of them. Ordinary matter is built from two kinds of quark, the ones we call up and down, arranged in threes to make protons and neutrons. There is a third kind, called strange, which is heavier and which decays quickly in every setting we can make on Earth. But a suggestion has been sitting in the literature since the 1970s that if you had a large enough lump of quarks with all three kinds present in roughly equal numbers, that mixture might actually be more stable than ordinary matter, not less, more, which would mean that everything you can see and touch, every atom in the Earth and the Sun and yourself, is not the universe's preferred arrangement of matter at all. It's a very comfortable second place, the warm room, rather than the true floor. If that's true, then the true lowest state of matter exists almost nowhere, because getting there requires assembling a great many quarks under conditions that only occur in the middle of a collapsing star. The barrier between the two is enormous, which is why we're all perfectly fine, and why an atom on Earth has never once been observed to slip into the other arrangement in the entire history of the planet. But inside a neutron star, where the pressure does the assembling for you, the conversion might happen naturally, and the result would be a different kind of object altogether. A strange star, slightly smaller than a neutron star of the same mass, a little denser, and held together not just by gravity, but by the strong nuclear force acting across the whole body of it, so that its surface would be a genuine edge, an abrupt end to the material, with no crust and no atmosphere at all. We have a handful of objects that raise an eyebrow. One or two that seem to be a little smaller than they ought to be for their weight. One that appears too light to have formed the ordinary way, sitting below the mass that a collapse is supposed to be able to produce. None of them is proof. Every one of them has an alternative explanation involving a neutron star with slightly unusual properties, and the honest position is that no strange star has ever been confirmed, and quite possibly none exists. But the possibility is worth keeping in the room because of what it would mean. It would mean that the matter you and I are made of, the matter that makes up everything anyone has ever built or eaten or loved, is a temporary arrangement that the universe tolerates rather than prefers, and that the real ground floor is hidden inside a few 100 million small dark objects nobody can visit. The most ordinary stuff there is, and the most extreme place there is, would turn out to be two settings of the same dial. And then there is the enormous quiet population, which may be the strangest fact of all of them. We have catalogued something like 3,500 pulsars, a good night's work for 60 years of astronomy. The galaxy contains somewhere between 100 million and 1 billion neutron stars. Nearly all of them are undetectable. Some never point their beams our way. Most crossed the threshold long ago, slowed past the point where they could make radio waves at all, and went silent, and are now simply drifting, cooling by a few degrees every million years, dark and small and quite impossible to find. When you look at the night sky, you are looking through a crowd of them. Between the stars you can see there are hundreds of millions of city-sized objects, heavier than the sun, spread through the galaxy like grains of sand through a house, and not one of them shows up on any photograph. So how close is the nearest one? The nearest we've managed to spot is a few hundred light-years away, close enough that its light has been on its way since roughly the age of sail. It's not a pulsar, it doesn't beam at us, and we found it only because it is still slightly warm and shows up as an extremely faint X-ray glow, a thumbprint of heat left over from an explosion that happened before people wrote anything down. There are almost certainly closer ones. There is no way at present to find them, and the arithmetic on that hidden population turns up something quietly startling. If there really are hundreds of millions of neutron stars spread through the disk of the galaxy, then in our own neighborhood, in the volume of space around the sun, there ought to be a fair number of them, and the nearest one is probably a great deal closer than the nearest one we've actually found. The estimates put it somewhere within a few tens of light years, possibly closer than some of the stars whose names you learned as a child. And we cannot find it, because a cold neutron star gives off almost nothing at all, and the search for something that small and that dark against the whole sky is a search with no good method. There is very likely a city-sized object heavier than the sun sitting in our immediate stellar neighborhood, and we do not know where. A few of them do announce themselves, though, by moving. The kick they receive at birth can leave them traveling at 1,000 kilometers per second or more, which is fast enough to cross the space between stars in a few thousand years, and fast enough that they plow into the thin gas between the stars and push it into a bow wave ahead of them, the way a boat pushes water. One of them, out in the northern sky, is doing this so vigorously that the glowing wave it's driving has a distinct shape, a rounded body with a long, thin neck of gas trailing behind, and it has been called the Guitar Nebula ever since somebody first looked at the image and saw the resemblance. It is an object the size of a town, moving fast enough to leave the galaxy, drawing a picture of an instrument in hydrogen gas as it goes. It's a good image to hold all of this in, something that spent 10 million years as a bright star, and 1 second as a collapse, and will spend the rest of eternity as a small dark ball, is passing through the emptiness at 1,000,000 miles an hour, and the only trace it leaves on anything is a faint shape in gas that nobody will be around to see fade. They will be there for a very long while. Long after the last stars have gone out, long after the galaxies have drifted beyond one another's reach, these things will still be sitting in the dark, cooling by fractions of a degree over spans of time that make the current age of the universe look like a rounding error. In the deep future, when there is very little left that anyone would call an object, a great many of the objects that remain will be these. The universe's most extreme and most compressed things also turn out to be its most patient. So that's the night. You watched a star run out of fuel and fall into itself in 1 second, at 1/4 of the speed of light, and you learned that the flash we can see across the universe is the leftover 1% of an event that spent the rest of itself on ghosts. You stood as close as anyone can to a surface where a marshmallow arrives like a power station, where the mountains are millimeters high, where the horizon curves up around you like a bowl and the clocks run a fifth slow. You went down through a crystal of iron and a kitchen full of nuclear pasta, and into an ocean with no friction at all, full of 1 billion tiny whirlpools that snag and slip and make a dead star stumble in its ticking. You pressed an armful of snow into a plum and then kept pressing. You met the woman who found the first one in 1/4 inch of untidy ink, and the 2 people who guessed they existed 33 years before anybody could look. You watched us take those corpses and put them to work, as the steadiest clocks anybody has, as the address engraved on a plaque leaving the solar system forever, and as the arms of an instrument light years across. And at the end you found the gold, and where it came from, and the fact that some of it very likely lives in this room. But underneath every one of those, there was one idea, and it's the one worth keeping if you keep anything. A neutron star is not made of anything unusual. It is made of exactly what you are made of, and what the snow is made of, in the same proportions, obeying the same rules, at the same weight. The only difference between that object and your hand on the blanket is room. You have room in you. Enormous, generous, cathedral-sized room. An emptiness so vast that all your solid parts together would make a speck the size of a single blood cell. And every bit of that emptiness is doing something. It's the space where electrons can move, and so chemistry can happen, where molecules can fold, where warmth can travel, where a cell can hold its shape, and a lung can fill, and a thought can cross. Squeeze the room out, and you get the strangest object in the universe, keeping perfect time, doing nothing, forever. Leave the room in, and you get a person, briefly, who can lie in a warm bed and wonder about it. There is nothing here you need to hold on to. Not the numbers, not the names, not the pasta or the whirlpools or the year of the guest star, all of which will go on being true whether or not anybody remembers them tonight. Let the crystal and the beam and the 14 lines on the plaque drift apart again, the way steam leaves a cup. Let your shoulders come down. Let your breathing find its own slow rate, the way that first star found its own way down, without hurry, sure of the direction. And if it's snowing where you are, or if it isn't and you'd like it to be, put the snow back outside the window, falling past the light, each flake almost entirely air, drifting down onto a field of almost nothing, in a room made of almost nothing, over a person made of almost nothing, and all of it holding together beautifully. And there's one last small thing to take with you into sleep. All night long, in every atom of you, an unimaginable number of tiny specks are sitting at exactly the density of a neutron star, quietly holding almost all of your weight, and around each of them a great deal of nothing is being carefully, patiently kept open on your behalf. Nothing has to try. It's just the rule, the same stubbornness that holds up a dead star heavier than the sun is, right now, holding your body a comfortable distance away from the sheets, holding the sheets away from the mattress, holding the whole soft arrangement of your evening in place while you let go of it. You are being held up by the most reliable thing in the universe, and it has never once, anywhere, been observed to fail. If you're still awake and you'd like one more journey, there'll be another one waiting on the screen to carry you onward. Otherwise, just stay here in the quiet, in all that lovely space. The stars will keep spinning while you sleep. Good night, Snoozenaut.